All right, how's it going, everybody? We are here on Thursday, February 4th. We are going to talk about section 1.8, linear differential equations and the integrating factor today. This is a super cool day. We're going to get our second analytic technique for solving differential equations today. So far, the only analytic technique that we've got is separation of variables. It doesn't handle a ton of cases for us. This is going to kind of broadly expand the number of cases that we're available of tackling here. This is also going to be a technique that's going to be useful for us once we get into our second order differential, or sorry, our systems of differential equations coming up in our next chapter here as well. So this technique's certainly going to follow us around a little bit here. I really like this technique. I like the concept behind this technique. The idea behind this is very clever. And it's so we're gonna derive our formula for it and use it to solve a new set of differential equations that we previously were unable to solve. So what we kind of want to remember, like kind of getting our context right here, in section 1.2, we got our separation of variables formulas that says, you know, given some differential equation dy dt equals f of y t, which very importantly needs to be able to be written as g of y h of t. We solve this guy as doing our 1 over g of y dy integral equals our integral of h of t dt, and then solve for y. All right. So this is our general strategy with separation of variables. Get a product of two terms, one with all the y stuff, one with all the t stuff. Get the y stuff with the dy, get the t stuff with the dt, integrate both sides. Hopefully we can algebraically solve for y, but certainly not always. One of our important things to recognize here is that when we perform this separation of variables, this one requires the differential equation to be separable. So it's a pretty narrow class of differential equations. It also depends on our ability to integrate twice, right? Not only do we have to integrate 1 over g of y, we also have to integrate h of t, and then we still hope to be able to algebraically solve. There's kind of a lot of limitations there, so we know that this is not, you know, anything that requires two different integrals. You should always be like, is that even going to work? Now, it's true that today we're going to see a pretty similar type of limitation here, dependence on multiple integrals to do this. But never stop kind of like counting how many integrals a process always takes. That always should make you say, like, can I actually do this if it's going to require that much integration? Integration's hard, right? So what we want to identify today is a new category of differential equations, right? A category meaning separable differential equations is a category. It's all the ones that can be written like this. Our new category today is linear differential equations. And what that really means when we say linear is there needs to be a linear y term, right? Not a derivative of y, not a y squared, not a 1 over y, not a square root of y, not a sine of y. We need to have a y term, a linear y term. That makes it linear in y. I don't care what all of your t stuff looks like. You could have a big old monster mess of your t component over there. What's really important to me is that there is a single y to the first power that is involved in our differential equation. Then we can consider this to be a linear differential equation. Um, Ultimately, this technique is going to have very close ties to the product rule for derivatives, and we're going to see exactly why. We're going to use this concept. We're going to try to undo the product rule to help make this guy happen here. And I guess what I kind of want to do is do this guy right here, just to make some brief statements here about things that are linear in y and things that are not. And so maybe I'll do some green and some red right here. For example, dy dt equals y sine t. This is linear because it has a y to the first power, and I don't care what sine of t is. It looks like sine of t is my g of t term right here, and r of t is 0. On the other hand, if I were to flip these guys and write dy dt equals t sine y, this is no longer linear in y because this is a trig term in terms of y. Y is a trig function there, not a linear constant, not a linear, like a polynomial term right there. It's also true, maybe I'll write one more over here, that dy dt equals negative 2y plus 8. You should recognize that this is both linear and separable. So this is one that we could solve using either technique here. Negative 2y plus 8, it is linear in y. Negative 2 is g of t plus 8 r of t. But it's also separable because you could just divide this whole dang thing over to the left side and integrate and get some like, a natural log of negative 2y plus 8 times the negative 1/2 or whatever we're going to get out of that guy right there, right? So just identifying what's linear and what's not linear obviously is going to matter right here. We're going to need to know what is your g of t term. Less importantly, we need to know what's r of t. This r of t term is going to come to play an important role. Trying to think into the future here. About 2 months from now, we're going to talk more at length about this guy. G of t is going to be one that we're going to focus on here today a little bit more as like playing an important role in the decision-making process associated with solving these linear differential equations here. So, let's take a look at this. What we're going to do is we're going to derive this general formula. What we want to do is we want to solve a general linear differential equation. So the only thing that I have done to this guy relative to what we originally started with right here is I modified this ever so slightly only by subtracting over the g of t times y to hang out with the dy dt. So notice that this is actually the first time ever that we're interested in expressing a differential equation not in the terms of dy dt equals something. Here we're kind of mixing and matching here, right? In a sense, we're doing addition subtraction to get all of the y components together on one side, right? So same setup as this. I've just shifted one term to the other side of the equal sign, and it looks like I'm calling negative g of t positive a of t. Tiny adjustment that we're making right there. But the bottom line is this way is going to be a little bit more helpful for us to visualize this because we want to look at this and kind of be like, what do we really see here on the left-hand side of our equal sign right here? And so I want to say some things. I've like heard some like funny ways to describe this process right here. One thing I can tell you is that this process wasn't discovered till quite a bit after differential equations had already become like a thing that was being studied in like the early 1700s. And it wasn't for, I don't remember quite what it was, something like 50 or 100 years before people kind of discovered this technique. This is sort of one of those things where you can kind of bang your head against the wall trying to solve this for a while. And then it's like one of those things where it's like once you see it, you see it. And it took just one smart dude to see it before this became an obvious thing. So in a sense, like I feel like if I tried really, really hard and worked on this for a long time, I could have figured this out on my own. I kind of like feel that like confidence in myself that I could have done this, and I think you'll kind of agree with this. The other thing I'd like to share with you before we get started with this is that I've had this explained to me by other like professors to say a good way to kind of think about what we're seeing here on the left-hand side of our equation is you should imagine, if you're a person of age, that perhaps you've had 4 or 5 or 6 beers and you're looking at this thing on the left-hand side, and I'm saying to you, hey man, what's this thing on the left look to you like? All right. And I want to say, and again, this is a very, very generic equation, but what does this look sort of like to you on the left-hand side over here? And you all have taken Calculus 1, which means all of you should be able to kind of see vaguely the thing that I'm seeing. And vaguely the thing that I'm seeing, I know it's only noon. Imagine that I've had 5 beers by now. If I'm a little bit fuzzy right now and I'm like, I don't know, man, I can't really do math, but maybe. What I'm seeing here is this. I'm adding together 2 terms. One of the terms has a derivative of y, and one of the terms has y being left alone. This should smell to you like the product rule from derivatives, right? It's not quite there. We're missing some parts that don't quite match up, but this should feel sort of maybe to you like this looks like it could have been that this left-hand side of this equation was an output from the product rule for derivatives. The derivative of one term is in one part of the addition, and then in the other part of the addition, that term is left alone with some other components in there, right? So our whole like idea, strategy for solving this thing is going to be to say, you know what? That left-hand side looks close to something like what you would get from using the product rule for derivatives. What I'm going to do is I'm going to get out my calculus beaten stick, and I'm going to make this thing be all the way the product rule for derivatives. If I can make that left-hand side be exactly something that you would get from the product rule for derivatives, then I can undo that product rule so that I just have the derivative of a product And then we can integrate on both sides to get rid of the derivative. And now we've just got a y left over for ourselves. So our strategy for this is going to be to say the left side sort of looks like the product rule. Let's incorporate one special term. The integrating factor is the name of that special term. We're going to need to introduce one additional special component that's going to get us all the rest of the way to this actually being truly a result from a product rule. Then we can undo the product rule. That's our broad strategy here. All right. So I'm going to say here, and there's going to be some writing that goes with this one. That's okay. Left side looks sort of like the product rule. We know what the product rule says. It says that if you take the derivative with respect to t of mu of t times y of t, what we should be getting is we'll leave mu of t alone. We'll get the derivative of y with respect to t, plus we'll leave y alone, and we'll get the derivative of mu with respect to t right there, right? There's our product rule. What our goal is to say, you know what, this looks close enough to this that I think I can force it to match up the rest of the way. So what we're missing in this, though, is it seems like we need a mu of t, right? So this is missing, right? So the whole point here is this. I really don't know what mu of t is going to be yet. We're going to figure that out later. But we're saying to ourselves, suppose you knew the perfect term mu of t that we did want to multiply through here, then we could make this look a little bit more like what that product rule is going to look like there. All right. So I'm going to then say, all right, so we've got mu of t times dy dt plus, it looks like we've got mu of t times a of t times y equals mu of t r of t. All right. So again, we haven't figured out what mu of t actually is yet. It's some unknown function of t. But if I could figure out what the right one is, the magic special version of mu, then by multiplying it through here, it looks now more like what we would get from the product rule here, right? So I'm going to say here, suppose we could find some mu of t. And we don't want just any old mu of t. We want it to exactly be the one that's going to make this be the product rule, right? I want to get my product rule statement right there, not just a single derivative. So what do I really want this derivative to be? Well, it looks like based on the statement that I just wrote right here, I want this. This is my desired output from the product rule, right? And the reason I'm writing that is because that's exactly what we're going to put right here. That's what we want to be getting out from this derivative right here. All right. So if we could find this mu of t, what our goal is to pick the special function mu of t that also has this property here as well as this property up here. That's how we're going to figure out what we actually want mu of t to be. Now notice, if we could find that, then we could rewrite the left side. Now notice, I am claiming that if we are able to come up with what this mu of t needs to be so that this is also true, then I get to use this equality right here to just substitute on the left-hand side. I'm going to say since this whole thing right here, mu of t dy dt plus mu of t a of ty, That's this expression right here. If that was equal to the derivative of a product of two functions, then I should just be able to make that direct replacement right here. That would say d dt of mu of t, y of t equals our mu of t, r of t, our right-hand side from up above, right? I'm kind of falling down from above right here. And notice we're in great shape now to solve for y. Now I can just go ahead and integrate both sides with respect to t. This just becomes mu of t, y of t, because we're integrating a derivative with respect to the exact same variable. This looks like an integral we're actually going to have to compute. But we have now solved in general for y, right? We've got our general format here for what this is going to end up looking like. So again, this is all dependent on our ability to actually know what that special magical mu of t needs to be. But it looks like, again, if we could find it, suppose we were able to find that mu of t, this is what our solving strategy would end up looking like, right? We multiply both sides of the function by the special mu of t. We recognize that the left-hand side is apparently going to look like the product rule if we pick the right mu of t. Since the left-hand side is going to look like the product rule, we can rewrite it as the derivative of a product. We can then integrate to undo the derivative and divide by the one term in the product that we don't care about to be left with the one term in the product that we do care about, right? So we've sort of outlined what our path is going to be for every time we solve one of these linear differential equations. But the one thing that's still missing is, so what the heck is mu of t going to be, right? All right, so we've got our solving strategy, but the one thing we skipped over is this line right here. Suppose we could find a mu of t. It's like saying, like, well, if somebody just handed you the correct mu of t, then you could do this strategy right here. What we need is a way for us to determine what mu of t needs to be on our own, right? So here I'm going to highlight some things for us right here. Let's pick ourselves a new color here, right? So this statement in green right here, I'm going to put two up arrows right there to indicate there are two places where we have made a claim about what we're looking at, right? Here is one way that we've described what mu's behavior needs to be like. Here is another place where we have described what mu's behavior needs to look like right there. And I want to use these two statements of what mu of t's behavior needs to be to determine exactly how we're going to get mu of t in each case right there, right? If we can come up with that, then that mu of t, which we will call an integrating factor, will be exactly the mu of t that we're looking to multiply through on both sides, right? So one of the things that we had said right here was that our derivative with respect to t of mu of t, y of t, needs to be equal to, and I just want to make sure I'm writing this exactly as it's up here. I did mu dy dt plus y d mu dt. All right. What I'm claiming then is that should be the same thing as what we think we must be getting out, the structure of how we need this thing to be, right? What also has to be true is if this really is going to be the product rule, then it needs to be from the derivative of the product. This is what we're actually getting out on the left-hand side. Mu of t dy dt needs to be adding mu of t a of ty. And again, this came from what we need this to work out as, like relative to the structure of the differential equation that we've originally been given, right? And so kind of the thing that I'm kind of seeing right away here is mu of t dy dt exists on both sides. So I'm just going to go ahead and cancel. It looks like we need y times d mu dt to be equal to mu of t, a of t, y. Well, looks like there's a y and a y I can divide away on both sides. I'm feeling pretty good about this now. So now I'm asking you the question, do you know a function mu that has this behavior? Well, it actually looks like we are in a, and I'm going to stop writing my like of t's right there just because we're trying to identify what mu is. So this is now saying, do you know some function mu where when you take its derivative, you get back mu, maybe times some extra stuff? And oh yeah, you do. Oh yeah, you do. I'm going to do some separation of variables right here. And we'll integrate. The natural log of mu appears to be the integral of whatever a of t dt is. And what's a of t? Let's pause for a second. What the heck is a of t? A of t is really easy. A of t is just whatever the coefficient was on your linear y term, right? So just identifying what's the coefficient on your linear y term, that's the a of t term. And so that's really easy for us to identify right there, right? So over here, it looks like all I got to do now to solve for mu is to exponentiate both sides. And we now know exactly how to pick mu. This term, mu, is referred to as the integrating factor. It's the factor that we want to multiply through the entire equation, because if we multiply that mu through the entire equation, it will force the left-hand side to truly actually be a product rule. And we can undo a product rule with an integral and solve for one of the factors in that product rule right there. All right. So here's our broad strategy. I'm going to talk through it and then I'm going to show you the short version. Our broad strategy is going to be this. We're going to say, you know what? This looks sort of like the product rule to me, but not quite. We're going to use a of t to determine what is the special value mu of t, a special function of t that we can multiply the whole equation by. That's what I've got right here. We multiply the whole equation by that mu of t. And by doing so, it's going to make the left-hand side get all the rest of the way to actually being the product rule. So we're going to rewrite it as the product rule that we know that it is. We're going to integrate both sides to undo the derivative associated with the product rule. And we're going to divide away the mu of t term that we don't care about to solve for the y of t term that we do care about. All right, that was my Tony verbal way. Now, don't worry, I did write it out in writing so that we can actually see this right here instead of just have me shouting stuff at you. So here's going to be our steps for all of our linear solving right here. We want to rewrite it in this format. We want to solve for what that integrating factor is going to be. Mu of t is e to the integral of a of t dt, which seems weird and difficult, but it won't be. We want to multiply the entire differential equation by that integrating factor, mu of t, to complete our product rule, to make things get all the rest of the way to truly being the product rule on the left. We want to rewrite the left side as the product rule and integrate to undo the derivative associated with the product rule. And then we're just solving for y. Let's see if we can do this here. This is one of those things that, man, feels like magic. The first time I ever did this, my mind was kind of blown. How does this work out to be exactly the piece that we need that's missing? It's great. So here we are. Let's do our first example here. I'm going to follow our 5 instructions. Step 1, rewrite our differential equation in this form, basically saying get all of your loose t stuff that isn't associated with y on the right, get your y term over to the left, maybe including some coefficients here, right? So we've got that our, in this case right here, I would say a of t is 2 over t. It's all of the coefficient. By the way, here's a little thing I should point out to you right here. The fact that this is a plus sign matters. If this was dy dt minus 2 over ty, then that negative would need to be incorporated with the a of t, or else you're going to end up with some sign issues. The product rule won't line up for you right there. So recognize that this general format does include the plus right there. You need to make sure that you're keeping all the coefficient on y associated with the a of t term. And we can see here that this r of t, which you might kind of think is the remaining terms right there, is that t minus 1 on the right. And notice that we didn't really use this. It will be involved in the integration that we're going to do, but that kind of just is along for the ride right there. We're going to see, as I said, we're going to see later this semester in about 2 months, we're going to give a proper name to these terms right here in association with our second order differential equations, and we'll see what role they play a little bit more carefully then. All right, so my step 1 is done. It was already given to me in this form. Step 2, find the integrating factor at mu of t. So I'm going to identify mu of t. It should be the e to the integral of 2 over t dt. It's my a of t term is what we're integrating as the power on e. So I can think of this as 2 times the integral of 1 over t dt. I know that this is just a natural log of t that we're going to get up there, right? Notice that in a sense there could have been a plus c that would come out right here, and that would give us like the ae to the 2 ln But notice that by multiplying this entire equation by an additional constant of a, that's not doing anything for us. So technically there's like a plus c that I'm just like ignoring here, which is sort of mathematically bad. But you also know that like multiplying that whole equation by 5, why would I do that? My next step would just be then to divide the whole equation by 5 to get rid of that extra constant multiple. So I am like skipping the constant of integration here, which is technically not correct. But since it provides us no value in the solving process here, multiplying the whole equation by 5 does nothing. I would just divide the 5 right back out again. So I'm just going to skip the multiplying by that constant multiple introduced by the constant of integration right here and leave it in this form. And now I'm thinking to myself, is there some way that I can better simplify this? Well, I do know that constant multiples in front of natural logs are actually powers. And I know that e to a natural log is really, those are inverse operations. So it looks like here our integrating factor, mu of t, is t squared. So the claim is by multiplying the whole equation by t squared, the left-hand side will become a true representation of the product rule, which we can undo. So I have found mu of t. And by the way, this is like usually about the hardest this ever gets. We'll see a pretty crappy mu of t in our last example here today, but usually this is a little uncomfortable, but not too terribly much. And honestly, you're going to get a little bit used to this. Every single linear differential equation, you're always going to solve by step 1, doing e to the integral of something and needing to algebraically simplify this. So like, if that was a little uncomfortable for you, I kind of get it, but also get over it is my statement that goes with that one right there. I get that that's a little weird, but you really need to remember your log properties and your exponentiation properties right here. It's going to come up every time here. So step 3 now says multiply the whole dang differential equation by this mu of t right here, and then recognize that the left-hand side is now the product rule. So now it looks like I'm going to do t squared times dy dt plus, when I multiply this by t squared, a t on top cancels with a t on bottom. So that's going to give me 2ty equals, don't forget to multiply your right-hand side by t squared. That definitely matters. Right? So I've multiplied by mu, and it gave me this. And what you, and again, our big conceptual thing to see here is that this is our product rule exactly, right? This is, on the left-hand side, we have t squared is left alone. We took the derivative of y. The right part is we left the y alone, and we took the derivative of t squared, and we've got the sum between them. This is exactly our like f g prime plus f prime g, right? I think is like the usual notation that we are comfortable seeing on that guy right there. By multiplying by, and again, I don't think any of you could have looked at this and been like, I think if we multiply by t squared, I'll be able to solve this thing. Like, you're just not going to see it, right? So that's why this integrating factor is super important, that we can actually solve for the integrating factor so that we end up in just automatically in a product rule scenario right here. So now what I can see is we can so let me follow my steps up here. We multiplied by mu of t. We've clearly completed the product rule. We can clearly see its parts right there. Now let's rewrite the left side actually as a product rule, right? So what this looks like to me now on the left-hand side is the derivative of, well, what are the two left alone parts? That's y was left alone and t squared was left alone, right? This should be f times g. Pretty nice and easy right there. Verify, stop for a second, convince yourself that this derivative does in fact give this left-hand side right there, and that we want to see that like sort of pull back into the product rule expression there. Now we're integrating on both sides. Integral on the left of the derivative cancels. Right, so the integral of the derivative is just the expression that we were taking the derivative of originally. And now we're in great shape. We're basically done right here. I just got to do a quick little polynomial integral and a division by t squared, and we got this thing. So I'm seeing 1/4 t to the fourth minus 1/3 t cubed plus c. And boy, oh boy, holy cow, are these plus c's going to be meaningful. What we're going to end up seeing here is in a lot of cases, the not necessarily so much right here, but in a lot of cases, this c term actually ends up carrying most of the action of our eventual solution. Because when I divide by this t squared now, notice we're going to get a ct to the negative 2 over here. And it's actually canceling away a bunch of the t action that we see right here. Really, dropping your plus c here is no longer just dropping a vertical shift. The c term often ends up carrying a significant amount of the action of our final result here. So really, really, really hang on to those guys here. And so I feel like I'm seeing here a 1/4 t squared minus a 1/3 t plus ct to the negative 2. We've divided everything by a t squared right there. I think this is a good general form for our answer. All right, so the magic that happens here with the integrating factor is we always want to see a sum involving a derivative and its non-derivative, dy dt and y, as being almost the product rule. By computing the integrating factor as e to the integral of the coefficient on the linear y term, that will always tell us exactly what we need to multiply by to force this to be exactly the product rule. And then we're just undoing the product rule and solving. All right, so this is a super cool technique. I feel like I don't know. In math, there's some like exciting formulas and some not exciting formulas, but this isn't a formula, right? This is like an algorithm. This is a broader strategy than just a formula. It's a multi-step process here. So don't think of this as a formula. Think of this as an algorithm. But this is, I don't know, this is cooler than other stuff that you learn how to do, I feel like. This is not just factoring a quadratic. This is like saying, I'm comfortable in this zone. I'm currently in this zone adjacent to that comfort zone. Let's get all the way into our comfort zone over there and then work with stuff that we previously recognize out there. And so this is pretty broad strategy in math a lot of times is saying, master the things that are doable, like the product rule, and then see what things you can force to be related to that because you've already mastered that one thing. So when things get hard, we try to relate things back to things that we already know that are easy. So this is kind of the general structure of what your work's going to look like on all these things. Get an integrating factor, multiply by it, re-express your derivatives in terms of a product rule, undo the product rule with an integral, solve for y. Notice that there's two risks here. One, that you won't be able to compute your integral for the integrating factor. That can happen. I don't know. We don't typically have too crazy of expressions sitting right there, but it also might be the case that you're not able to do this integration on the right-hand side. That's another potential limiting factor. The third potential limiting factor is, can you always actually undo this, like actually do the solving for y right here? Sometimes it's easy to get rid of this partner term. Sometimes it doesn't fold in nicely over here. So there's always still going to be some of these potential calculus algebra limitations, just like we've seen with our other formats, but that's integration for you. So we'll see kind of how that plays out for us here. But we got our first example. So let's do a couple more here. Let's do another kind of simple example, and then we'll return to a slightly tougher example that'll take a little bit more work here. So this one I think is not going to blow our minds too much right here. Let's see if we can follow our process here without having to kind of reference our instructions, right? So first things first, I want to get all the terms involving y over to one side. By the way, notice with this one, we'll solve for c at the end. We've been given an initial condition. So step one, let's get all our terms involving y over to one side. Step two, let's solve for our integrating factor. I see this on the left and I'm like, ooh, that is almost a product rule right there. Let's get it all the rest of the way. By the way, what I'm seeing is I want to have some function where when I don't take the derivative, but I do take the derivative of the missing part, it pops out an extra 5. Do you know some function where when you take its derivative, it pops out a constant multiple of 5? Let's see. Well, this is our a of t term is just 5. So all I'm integrating is 5 dt. Well, this was a pretty easy integrating factor. There it is. Let me say this again, by the way, real quick. I am hoping that you guys are sitting there being like, Tony, that should be a 5t plus c, right? And if we did go do this, we'd get like an ae to the 5t, where a is just some unknown constant. But again, recognize that if we multiply the whole equation by ae to the 5t, then all we've done is introduced an extra constant multiple of a everywhere. That isn't helping us with anything. So then my very next step would just be to divide both sides of the equation by a to get rid of it again. So that's why I am not interested in accumulating that term right there, because I would multiply by it and then immediately divide by it. So I'm just skipping it instead. All right. So this says to me, let's multiply the whole dang thing by e to the 5t. Sometimes I write this with my technically bad math notation of throwing a whole equation inside of a parenthesis, because that's how I roll. Right there, right? So we're multiplying the whole thing by our integrating factor. On the left-hand side, this gives me e to the 5t dy dt plus 5e to the 5t y. Notice, by the way, I'm doing this ever so slightly unnatural ordering of my multiplication. Like, I don't think that any of you guys would multiply 5y by e to the 5t and stick the e to the 5t in the middle like that. Isn't that kind of weird? I like pushed apart the 5 and the y and mashed that into the middle. The reason I'm doing that is because I know in my head I'm making this look like a product rule, right? That's like I'm anticipating that product rule-ness of this. So I see that 5e to the 5t is our derivative of e to the 5t. dy dt is our derivative of y right there. So like slightly weird that I would write it in that order, except that I know what I'm looking for when I do this, right? So I'm going to now rewrite this left-hand side as the product rule that I can recognize it as. This looks like just y times e to the 5t, right? Now over here, it looks like, it looks like we've got something that's a little bit tougher right here. It looks like I've got my, I know I'm going to have to integrate this, can I? Let's see if we're good enough to do this. I want to integrate on both sides here. Y e to the 5t equals the integral of e to the 5t sine of t dt. So in a sense, I could solve for y here right away as saying like it's e to the negative 5t times the integral of e to the 5t sine t dt. So in a sense, I like have my answer, but there's still an integral in it. Unsatisfying. Let's see if we can do this integral. I'm hoping that all of you remember the fact that you took Calc 2. If you don't, you're in trouble. I'm going to reorganize my integral ever so slightly. And I am thinking to myself that I want to do a little bit of integration by parts. I am going to pick u as sine of t. du, therefore, will be cosine of t. I'm going to pick dv to be e to the 5t dt, and therefore v must be 1/5 e to the 5t. This is going to allow me to rewrite this guy as, I honestly kind of want to get all of this in here so that we can make sure that we see the magic that's happening here. So it should be uv minus integral v du. There's a dt right there. V du, I got the 1/5, I got the cosine of t, and I got an e to the 5t dt. And now I look at this and I say, well, I can't do that integral either. I need to get some more integration by parts going on. So I'm going to set up basically the same thing. I'm going to say u equals cosine of t. Therefore, du is negative sine of t. I'm going to pick dv to, therefore, if I pick u to be cosine, then dv needs to be e to the 5t dt, and v needs to be 1/5 e to the 5t. So now I've got for myself an integral of sine t e to the 5t dt equals 1/5 sine t e to the 5t minus 1/5. And now I have uv. So I'm going to get a 1/5 e to the 5t cos t minus integral of v du. And that's going to be a 1/5. I'm going to make this a plus sign since du has a negative on it, so I'm subtracting off a negative. And I'm getting e to the 5t sine t dt. I know I'm falling off my edge right here, but the ever so important thing is there's another integral, but it's actually equal to our original one that we wanted to evaluate here. So let's go ahead and clean this up a little bit. It looks like I should be getting a negative 1/25 right there and a negative 1/25 right there. Maybe I think I can go ahead and say if that's a negative 1/25, I'm going to add it over to the other side here so I get 26/25. 1/25 e to the 5t cos t. And therefore, I can multiply the whole thing by 25/26, and I think we've got ourselves an answer here, which is, whew, that took a little bit of work right there, but that's okay. We got this thing right here. So our integral of sine of t e to the 5t dt equals, I'm multiplying by 25/26, so that's going to leave me with a 5/26 sine of t e to the 5t minus 1/26 cos t e to the 5t. And now this can go into our solution right here. So it looks like I'm going to get as my final answer y equals, I'm going to multiply everything by e to the negative 5. Oh, by the way, hold on. Oh no, and that's where I'm going to get my plus c out of this integrand right here, right? So we're getting our plus c that's going to be associated with this guy here. So I think that I should be getting, let's see here, 5/26 e to the, wrong terms. So notice as I multiply e to the negative 5t times these terms, it cancels the e to the positive 5t. So those actually go away. So as promised, the c term is actually holding all of that exponential behavior that's associated with my general solution right there. All right? And it looks like that's going to now be our general solution to this guy. So this one's certainly a little bit tougher. Remember this integration technique, this double integration by parts. I've heard this referred to as dump truck integration, where you have to do integration by parts once, do it a second time so that our sine term goes to cosine, goes back to sine, so that we can combine our two integrals to have said that we've solved for it in a sense right there. So certainly I did some shorthand versions of some of these things right here. But again, this is we've managed to come up with our general solution to this guy right here. It makes sense to me that trig terms cropped up because we had some trig terms floating around in here that we're going to need to be dealt with. But that constant multiple of 5, so there's got to be some exponentiation that's also happening here since that's what relates y to dy dt. And we got all the parts that do involve these terms sitting right here pretty nicely. So, man, that's kind of... I actually kind of feel like our we should almost just check this right here. Here my dy dt is going to be 5/26 cosine t plus 1/26 sine t. Let's see, and we're getting minus 5c e to the negative 5t. The claim is that that was equal to negative 5y plus sine t. And here that means I'm going to get negative 5 times this, which is negative 25/26 sine t. Negative 5 times this is positive 5/26 cosine t. And negative 5 times y is going to give me a negative 5c e to the negative 5t, and then plus sine t. Well, it looks like my 5/26 cosine t and 5/26 cosine t match. Negative 5c e to the negative 5t, negative 5c e to the negative 5t, and look what's left over. Negative 25/26 plus 1 gives us positive 1/26 sine t. So it looks like our check works out here. Honestly, kind of unbelievably, right? Man, you just can't guess these solutions here. And that's why I find these to be so satisfying right here, right? So our check here was good. Pretty cool. Pretty dang cool right here. So, again, recognize the integrating factor part of this was pretty easy. Getting mu of t was easy. Multiplying it, recognizing the product rule, integrating, even getting to this step that involved the integral is pretty easy. The meat of this problem, the hard work of this problem was actually doing one of the integrals, right? And that's very, very regularly the case. We know that actually performing the process of integration, when it's not just undoing a derivative, is always something that's sort of risky in the sense that we might not even be able to do it. This is one of the harder integrals that we're all capable of doing here, our dump truck integration. So again, if you've forgotten your calculus from 50B from integral calculus, you might be in trouble because it turns out we still need all of these integration techniques to make this stuff happen right here. But I hope that you find this as highly satisfying as I do right here, where it's like, holy cow, all that stuff like really did work out there really nicely. And again, if you see an answer that looks kind of as crazy as this, you should be checking your answer because checking just involves taking a derivative and seeing if stuff cancels appropriately or matches up from left to right. Like, not really asking too much to check right here. You should be doing it for yourself so that you can be like, yeah, I know that that's the correct answer. I plugged it back in. I verified my solution right there. Oh, I guess our one thing I didn't do is I did not apply y of 0 equals 1. Okay, okay. I'm just going to say it. Plug in 0 for t, plug in 1 for y. We're going to have y of 0 equals 1, our solution associated with the c right there. I don't think throwing an initial condition is tearing us up too much right here. All right. So let's look at one more good example here for the day. Let's take a return to our mixing problem here, get a little bit of an application with this guy here, and see how upgrading our mixing problem to include a new component is going to introduce to us something that's going to require an integrating factor. Here we'll see a kind of ridiculous integrating factor that we're going to get for this problem right here. It turns out, though, it does not necessarily make this problem too much more difficult, even though the integrating factor is pretty wild. Also, by the way, I just got to share with you guys a kind of funny thing on this one right here. I'm just telling you a brief story. As I'm like looking through my handwritten notes for this one right here, I have all of this solution written out by hand in my notes. Right, like my notes has all these steps in this guy right here, so I can like look down and like make sure I'm not making mistakes. In my notes for this one, all it says in my notes is just this right there with no work whatsoever. I just have the next example written after that. Apparently, I trust myself enough to be able to do this process over here and get this right. And I kind of laughed and I looked at this and I was like, oh, I'm okay. Tony trusted himself a year ago when he taught this. There's none of this was in my notes. That was just implied, whereas all of this was in my notes as if I was going to struggle with this part right here. Kind of questionable note taking, perhaps on my part right there. Don't worry, I'm not going to screw up the mixing problem because I did write this one out as well. So, as we've seen with our mixing problems, kind of our big key for this is pay attention to units. Units have guided us on these application problems. Units are your guide. If you're really an applied mathematician, then you stick a unit on everything and you let them guide you through all of your problems here. We're all applied mathematicians because we're taking this class. Follow your units. So here's our scenario. We have a pond, and this pond has a volume of 10,000 cubic meters. That's actually, well, it's actually kind of a lot in a sense. Maybe it's not a huge pond, but that's an unbelievable amount of water in another sense. There are two inlets going into this pond, which we'll call A and B, and one outlet C. So if I'm going to draw myself a little pond here, I've got my one inlet here, A. I've got another inlet here, B. They're going into the pond. And we've got one outlet here, C, that's coming out of the pond out here. Right, so these are going in, C's going out right there, right? Typical ponds, they got to get their water from somewhere, right? So stuff coming in, stuff coming out. Initially, pre-humans, inlet A is going to bring in 500 cubic meters of water a day. B is bringing in 750 cubic meters of water per day. And very importantly, notice that C is removing exactly as much as A and B are bringing in, right? So the important thing for us to see here is that there's never any change in total volume of water in this pond. It's going to maintain exactly 10,000 cubic meters of water in our initial scenario. The amount coming in is equal to the amount going out, so the total volume is unchanged. Then humans are going to come along, as we do, ruin everything for all the natural ecosystems that we arrive at here. So now our things are changing. Apparently, A is near a road, and I think there's some absurd statistic that's something like, and maybe I'm exaggerating this slightly, but not by much. I think it's something like 50% of all of the salt produced on Earth is used for roads in the United States only. Think about whether or not that seems reasonable to you for all the waterways that all that salt is flowing into. Now stop thinking about it because it's depressing. Okay, so water from A is going to include road salt. And it's going to have 5 kilograms of road salt for every 1,000 cubic meters of water. And we're going to go ahead and do the thing that we sort of always have to do and like assume that this is a homogenized mixture, that it's well mixed, that it's not like all sitting near A. Certainly this gets into a much, much bigger mixture problem in that there's not going to probably be a uniform distribution in the pond. We're assuming that once the salt gets into the pond, it's all well mixed. Otherwise, this is going to be kind of beyond our grasp here. Water from B isn't near a road. Thank goodness for B inlet. Oh, wait, never mind. It's just going to be near the dump. So it's going to include a bunch of trash. 50 cubic meters per day of trash is going to be coming in. Now, the difficult thing about trash, if you guys have ever seen a pond, is that all it takes is a couple sticks here to be sitting at the outlet at C that know that the trash kind of gets stuck and it's stuck right there, right? So our assumption with this is that once this trash flows into the pond from B, it doesn't really have a way to flow back out. It's just going to settle at the bottom of the pond. So what you need to recognize now is that since this pond really only has 10,000 cubic meters of capacity available to it, what that means is that this trash is now taking up space that used to be taken up by water in the pond, right? So what's going to happen over time is the actual volume of water out of all the volume in the pond is going to go down because the volume of trash is going to go up. The only thing we need to account for now is it seems like if we're going to maintain exactly 10,000 cubic meters of overall volume, which is now both water and trash, if we're going to maintain that constant volume of the pond, then output from C needs to increase by 50 cubic meters per day up to 1,300 cubic meters to account for the trash, right? Because now we've got more than, now we're bringing in 1,300 total cubic meters of stuff. 1,250 of it's water, 50 of it is trash. So we're going to increase the output from C, again, to make sure that the volume in this lake is remaining the same, right? So here's what we want to do, our steps. First, let's try and even just building the ordinary differential equation here is tough. Let's build the differential equation that describes the change in amount of salt in the pond over time. Let's solve the equation if we can. Let's graph the solution that's associated with there being initially no salt. At time 0, there's 0 kilograms of salt. And my extra question here is going to be this. Notice something weird that's going to happen here. And I'm kind of alluding to it with this question right here. My question is, after how many days will the amount of salt reach a maximum? And what I'm hoping is that you, the mathematician, is saying to yourself, how do we even know that it's going to reach a maximum at all? How do we know that this function is going to have a maximum value? What if it's just one of these logistic curves right here and it just maxes out at some kind of like equilibrium value for amounts of salt because there's stuff coming in, stuff going out? It's what happened in our last mixing problem. What's the domain of this problem really going to be? You should stop for a second and think about this on your own instead of just letting me say this for you right here. If you need to pause the video, do that. Um, does it make sense for me to talk about what happens as t goes to infinity here? And I've highlighted this for a reason. If every single day 50 cubic meters of trash comes into the pond and doesn't leave, and if the pond always only holds 10,000 cubic meters of stuff, where stuff is water plus trash, what's eventually going to happen? Well, it seems like eventually there's going to be so much trash in the pond that there's not actually room for water to come in anymore, right? Because if every day we add 50 cubic meters of trash and it never gets removed, and the volume of the pond is constant over time, then that volume of trash is replacing the water over time until eventually it's just a scoop of land removed with trash in it. This is literally just becoming a landfill over time. So, what is the domain of this problem? How long does it take until this is just an all trash pond, right? Well, we've got 10,000 cubic meters of water initially, and we're going to lose 50 cubic meters of water per day, right? And my question would be, where is this going to hit the value of y equals 0? So, one thing to recognize is that our domain for this problem is it doesn't even make sense to talk about there being salt in the pond beyond 200 days. Because after 200 days, there's literally not going to be any water in the pond anymore because it's full of trash by now, right? So it seems like our function is going to start with 0 salt on day 0. It's going to end with 0 salt on day 200. But we know that we're going to accumulate some salt in between there, right? And so that's how I know that this should reach a maximum at some point in time. But I don't know what this shape is going to look like, and I certainly don't know where the maximum is going to happen. But I know for sure that if this is our salt axis and this is our time axis, I do know those 2 points for sure, right? But there's got to be some function out there. I don't know what the shape of it looks like. I don't know where the maximum is. We want to determine those things now. But I know that at days 0 and at days 200, there's no salt in the pond because there's either a fresh pond that humans haven't touched or there is no pond anymore because humans have literally filled it with trash. All right. So our domain for this problem is time 0 to 200. Doesn't really make sense for us to interpret our differential equation outside of that range anymore, right? So let's go ahead and see if we can build the differential equation, solve it, apply the initial condition to get a particular solution, graph it, use the graph to answer our question, when did we reach that maximum, right? We can kind of see my soft maximum on my sketchy graph right there, kind of do a little bit of interpreting there. So what do we got here? Well, we want to describe the change in salt over time, right? So we want to think about our word equations right here. I am thinking to myself that this change in salt should be our ds dt. So notice this is measured in. This is salt, so it's measured in kilograms. This is dt, it's a measurement of time. So this is kilograms per day. Maybe I'll get rid of that S right there. Oh, whatever, it doesn't matter. Kilograms per day. Kilograms is the numerator, days is going to have to be the denominator. So what that says to me is that this must be the units of salt in and salt out. Because it wouldn't make sense otherwise to add or subtract any other units to get to kilograms per day. So salt in has to also be kilograms per day. Salt out also has to be kilograms per day. All right. So let's see if we can find these guys here. So how much salt is coming in each day? All right, back up to our problem up here. I'm seeing that road salt only comes in from inlet A. It looks like we're getting 5 kilograms per 1,000 meters cubed. But what I know is that I have to be measuring this in kilograms per day, right? I currently have kilograms per meter cubed. So what I know I need to do here is multiply by some number of meters cubed per number of days. And I'm wondering, do I have that information? Well, yeah, this was our original information that was associated with this, right? 500 cubic meters per 1 day. That's exactly what we were originally told about this thing right here. It's just got salt now mixed into it, right? So I've been given this information, 500 meters cubed per 1 day. So that's going to give us 2,500 over 1,000, also known as 2.5 kilograms per day of salt. Cool. So we got one of them right there. We got our salt in. Now let's go ahead and look for our salt out. This one's going to be a little bit trickier, right? So what's going on with our salt out? Well, very similarly, we can think where's things going out from the pond. The only outlet is C right here, and it looks like C is going to be putting out this 1,300 meters cubed of water per day, right? So 1,300 meters cubed of water per day, but that doesn't really describe the salt content to me, but that seems to be one of our factors here. There's going to be this 1,300 meters cubed per 1 day. But again, I want kilograms per day, right? So I've got days on bottom. That's fine. I want to leave that alone. I want to get rid of my meters cubed, and I want to introduce kilograms, right? So now the question is, how much salt is going out per like what's our like density of salt in the water right here? I need to know kilograms per meter cubed. Well, I know that there are a total of S kilograms of salt in the water total. And what's our volume of the pond? Now, this is where you need to be careful. I think that a lot of people would be tempted to tell me that the volume of the pond is 10,000. But here's the difference. This 10,000 is the total volume of the pond. But what we know is that the trash isn't holding salt. All of the salt is held in just the water associated with the pond, right? I have a formula for how much water is available in the pond right there. That's how much water is going to be in the pond after T days. That is how much water is holding the S kilograms of salt that we've got. So what I'm seeing here is it looks like there's actually a whole expression of T involved with this, right? It's 10,000 minus 50 T. That's how much water is actually in the pond on day T. All right. So our salt amount is S. Our volume any given day can be computed by 10,000 minus 50t. Our good thing is that we've got our units to cancel just like we wanted. So it looks like what we're seeing here is 1,300s, trying to make that like a script S so it doesn't look like a 5, over 10,000 minus 50t. And this is a measurement of kilograms per day. Right? So a little bit tougher for a salt out expression right there, right? Two different variables are involved in this because the amount of salt is exactly what we're trying to describe. That is the variable of interest, salt. And our volume is changing because the volume of water in the pond is different each day. So we're coming up with a descriptor that is a day by day descriptor right here. So it looks like we can now write our differential equation. We know change in salt is the SDT. We know that our salt in is just a constant of 2.5. We know that our salt out involves both the variables S and T. Now, this is where I drop my units because I have already confirmed that 2.5 is a measurement of kilograms per day. I've already confirmed that 1300 S over 10,000 minus 50T is in kilograms per day, just like DSTT is in kilograms per day. Without my units, I literally don't know how to do this problem. You got to use your units to guide you along the way here. How was I supposed to know what I was supposed to multiply by here? Only by starting with a known quantity that had to have been involved, asking myself, what units do I want to get rid of? What units do I want to keep? I wanted to keep the days. I wanted to get rid of the meters cubed. I wanted to introduce kilograms. It guided me. It told me, my units told me how to do the problem, right? I don't have to think. Let the units do the thinking for you. So my salt out here is going to be the 1300 S over 10,000 minus 50T. So what we can see here is that this looks to me to be a linear differential equation in S. It's linear in S. It's definitely not separable. And something that always ruins stuff being separable is having an addition of a constant, addition or subtraction of a constant. That 2.5 right there really makes it awfully tough for things to ever be separable right here. So I know I couldn't have solved this problem using our previous techniques from section 1.2, but since this looks to have just a linear S term in it, I think that we can handle this guy. So now I'm on to using my integrating factor to solve this differential equation here, all right? So I'm going to do two things right here. One, I know I want to get all my S stuff pushed over to the left side. Two, I know that I want to think about this 1300 over 10,000 minus 50 as a coefficient on a multiple of S is a slightly better way for me to think about this right here. I'm also seeing, by the way, I feel like I could I don't know, simplify this a little bit right here. If I divide this whole thing by 50, I think that's my easier way to write this term right here. So thinking of this term in terms of my reduced fraction right here, I'm going to move the S out front so that I'm thinking of the 26 over 200 minus t as a coefficient. And I'm going to push it over to the left side to hang out with ds dt. Plus 26 over 200 minus t times S equals 2.5, right? So I'm doing my upfront work, right? The work to get it into the format that we want to see it, simplifying fractions, thinking of terms as being coefficients on other terms right here. I've now got that this is my a of t term, right? My coefficient on the s right there. So it looks like we can go ahead and compute for ourselves an integrating factor. Is it going to be nice? It doesn't quite look like it, but that's okay. We don't need things to be nice. We just need them, right? So mu is e to the integral of a of t dt, which is e to the integral of 1 over 200 minus t. I'm pulling that 26 as a constant out front. That's a dt. That's going to be a natural log right there. So we're going to get an e to the 26 times the natural log of 200 minus t. But I'm also seeing we should be popping out a negative from the chain rule right there, right? That negative on the t would have popped out the negative right there. I don't need my plus c right here because all it would introduce is a constant multiple that I'd be multiplying everything through that we don't need. And so now I just want to clean this up a little bit more. Again, I'm remembering that any coefficient on a natural log can be a power on the natural log instead. And now I'm seeing e to the power of a natural log. Those cancel, just leaving you with the original expression here. So it looks like this is just going to be 1 over 200 minus t to the 26th power. So as promised, we're getting a pretty ridiculous integrating factor right here, right? That's not necessarily something that we are generally super comfortable with right there. A rational to the 26th power with like a difference of t down there. Ugh. But let's see if we can like kind of make this guy happen right here. And I guess I want to maybe, since I'm about to multiply by this thing everywhere, I don't want to introduce a fraction. So I think I'll use the negative power version of that guy right there. Either one of those would be fine, right? So let's pop back into our differential equation and see if this is gross too gross or if we can handle this right here, right? So 200 minus t to the negative 26 is what we're multiplying everything by. Ooh, and here's the thing I think maybe I want to do for myself. Now that I'm seeing that there's going to be powers of 200 minus t, I'm thinking to myself that 200 minus t right there, that's probably a nice thing for me to rewrite that as 26 times 200 minus t to the negative 1. That might be nice for me right now. And again, just kind of highlighting some things right here. There's our multiplication, there's our multiplication, there's our multiplication right there. All right, so we multiplied the whole thing, all three of the general terms that were in there, by our integrating factor, 200 minus t to the negative 26th. This is really just a rewritten version of what we originally had right there because I'm recognizing that I'm probably going to want to combine some terms. So let me just do a simplification line right here. And it looks to me like we should be seeing some 26 times 200 minus t to the negative 27 s equals that 2.5 times 200 minus t to the negative 26. And notice this feels to me exactly like kind of how we get these terms out from derivatives, right? This looks to me like the derivative of that 200 minus t to the negative 26th. The negative 26th popped down, the negative popped out from the negative right here from the chain rule to make that a positive still, and we reduce the power by 1 to go from negative 26 to negative 27. This is exactly giving us our product rule expression right now. So what's in the product rule? Well, it looks like s was left alone and the derivative of s. So s is one of our terms. The other thing you can kind of see here is that it just has to be the case that this is our other term, since this must be the left alone term since it's partnered with the derivative term, if we're thinking of this as our product rule right there. So it's got to be that this is our 200 minus t to the negative 26th. Not really nice, but technically doable. And this is going to be equal to 2.5 times 200 minus t to the negative 26. All right. So we've rewritten this. We've rephrased this as a product rule. Let's integrate on both sides. And I'll be nice to myself and put that 2.5 out front. And now I'm looking at just here, just a power rule for my integral. This is doable over here. What are we getting from this guy? Well, this is just a power rule with, we know that we're going to get a little, I'm going to skip the u sub, but all it's going to do is pop out a negative. I'm going to add 1 to the power to get negative 25, and therefore I need a negative 1 over 25 to cancel that out. This negative that's right here, though, is going to become positive because there's two negatives that were introduced. One negative from bringing down the coefficient out front, making that a negative 1 over 25. One negative that's popping out from a u sub that we formally would be doing right there from the negative t. And both those are combining to make that a positive term that we're getting right there. And never forget your plus c. And man, we're almost there. Oh man, I gotta scroll way down here. Anything else? Okay. But we're almost done. We basically got this guy. Let's just clean. We're just doing algebra by now. We're just cleaning up. So 2.5 over 25 is just 1/10, right? I'm going to just write this guy as just a plus C right there. I'm letting the C absorb that 2.5. I don't care. C is a basket that's holding all of your constants. We'll solve for C in a second. And as my last step, it looks like all I've got to do is multiply everything by 200 minus t to the positive 26 power. And what that's going to leave me with here is S equals 1/10. Notice when we multiply by the positive 26 power, we're just left with one of these. Just a linear term right there. But notice all the heavy action is associated with our C term. A 26th power out there. Ridiculous, kind of. But we're going to see this is going to completely like satisfy what we are ultimately looking to see for our graph up there, right? We drew this graph as like our sketch. We're going to see that this is not too far off right here. All right, so coming down here, all we really have left to do now is set S of 0 equal to 0 and see what we get for C. Oof. So we subtract this guy over right here. Oh, that's a gross term. 200 over 10, which is just negative 20 right there, equals C times 200 to the 26th. So I'm dividing by 200 to the 26th. So I guess I'm getting, oh, wait a minute, how am I? Okay, so that's negative 20 over 200 to the 26th. That's one of the grossest C's I've ever solved for in my life. But we can go ahead and slap that into our equation here and get our overall S of t equation. Minus, and notice one thing though here, this C term has a 200 to the 26th. C is multiplying other stuff that's to the 26th, so it actually seems like maybe there's like a vaguely clean way to write this. At negative 20, I'm going to kind of keep out front, and then we'll get a 200 minus t over 200, all to the 26th, right? 200 to the 26th is on the denominator from C. Sorry, 200, oh yeah, and then 200 minus t to the 26th is in the numerator because it was a multiplicative term right there, giving us our final general form answer right here. Whoo! That was some work right there. That was some effort to build that. That was some effort to solve that. Excuse me, that was some effort to get an integrating factor. That was some effort to apply the integrating factor and undo the product rule. That was some effort to do the integration and solve for S. All these parts here were a little bit wobbly because who the heck deals with rational functions to the power of 26? It seems like it naturally arose right here. So now you should be saying to yourself, wow, that seems unbelievable. Let's see if this is actually going to kind of give us what we want. Now, before I go graph this guy in Desmos, I want to show you kind of how we can kind of visualize what this function is doing. You should recognize that 26th powers make things kind of go crazy, right? What I know is that numbers that are below 1, when we take high powers on them, are going to get crushed down towards, or excuse me, so when we take large powers on fractions, they get smaller, right? A half squared is a fourth, a half cubed is an eighth, a half to the fourth is a 16th. They're getting smaller and smaller and smaller because it's a number less than 1, right? I'm recognizing that this fraction is always less than 1, right? So what I'm seeing here is this. When our times are very, very, very small, our times are very, very, very small, like day 1, this fraction is essentially 1 at day t equals 1. This fraction is almost 1. So even when we take the 26th power, we're going to get out about 1 from all this stuff. So we're really just subtracting off about 20. At day 1, this is also going to be like a 20. And it seems like our salt component then should really just be like our day's difference from 20. Basically meaning it should be a linear component that we're experiencing there. Right? Now, on the other hand, once our t's get out closer towards 200, this is all going to go towards 0. And what we should be seeing then is a decline that's based on this linear term right here. And so we're going to see in our graph, we're going to get some like two different parts of this that are going to kind of seem like some linear parts of this, some growth and some decay based on whether we're keeping most of this term in the minus 20 or keeping almost none of this. It's almost like this is like a light switch because this power is so high. It's like you're either basically getting out 0 or 1 from this t term over here, meaning you're either keeping your subtraction of 20 or you're not. Is in a sense what this is going to do for us. So let's see what this graph looks like in Desmos here compared to our guess of what we should be seeing. There was one last question that we didn't answer, which is what is the amount, after how many days will the amount of salt reach a maximum out here? That was the last thing we wanted to answer. We'll get that guy from a graph. So let's pop over to Desmos here and see what we can see. So I am seeing here, oh, I didn't bring up my Desmos already. All right, 1 second. Desmos. All right, if I pop over now, yay. All right, so I've got the equation. Y is going to be S, T is going to be X. Our equation that we ended there with was 1/10 200 minus T, minus X, minus 20 times 200. Oh, let me just make a, oh, come on, just quit being stupid to me. 200 minus x up in the numerator, 200 in the denominator, all to the power of 26. Oh man, I feel satisfied. Oh, that's good stuff right there. All right, so let's make this go just to get some visualization right here. And honestly, like if I make this go even further, I feel like it's a little, well, okay, 10,000, too much right there. But what we can see here with this graph is we're getting kind of that action that I kind of alluded to right there, which is notice how incredibly linear this graph looks. And that's because when we plug in x values that are large enough, this fraction is small enough that when you apply the 26th power, it essentially goes to 0, leaving us just with this component of the graph that we've got right there. So notice, for example, if I just copied just this, that's like what we're asymptotically approaching, right? Once x gets big enough, this whole expression is essentially going to 0 because it's a small fraction to the 26th power. All of these terms where x is very small is where this fraction is close enough to 1 that taking a 26th power still leaves you with like an essential like component to it right there. And it's subtracting off some amount, which is why these function values are less than the blue line, where the blue line is our first component right there. So like I said, any function that you ever see that has a number in here that is maybe less than, that is dancing around being near 1, a 26th power is basically like a light switch. And let me kind of show you what I mean by that right here. When we talk about functions having huge powers, it's like a light switch, right? It looks like this function basically gives us 0 as the output for most of the time, until it basically gives us out 1 as the output eventually, or a lot, right? It's on or it's off. Here it's off, and it basically just like switches on. It's almost like it's a discontinuity right there. And in fact, we could just do this. Notice what happens. When you put huge even powers on things, it's essentially a light switch function. It's off until it's on. Even numbers like 0.975, Desmos literally tells me you get out 0 when you take it to that large of a power because it's getting crushed down so much by that high power. And then immediately it can't even evaluate any points on this line that are up there because they're going to be so big right there, right? So that was our like little light switch function right there that says if, well, no, let me maybe turn these guys back on here, right? That says if we are looking at stuff that is a number smaller than 1 enough, the 26th power makes it go to 0. This whole term goes to 0, and our function effectively just looks like the linear for the remaining time out there. So there's some interesting sort of red flags that you should see anytime a 26th power or something like that is involved in one of your solutions. You should know that stuff between 0 and 1 will behave like it's 0 to the 26th power, whereas stuff that's much, much closer to 1, like our early days here, days like 1 through 6, are going to be actually having some substantive value to them. So we came over here looking for our final answer. How much salt is going to be in the pond, or excuse me, after how many days does the amount of salt in the pond reach a maximum? And it looks like at about 24 and a half days is the most salt that there will ever be in the pond. The reason why there's less salt later is because there's literally not enough room in the pond for there to be water because there's so much trash that's in the pond right there. All right, so based on a Desmos graph right here, I think we can see that and in fact, I think what I'll do just for the sake of our viewing right here, let me just fix this window. I just want to be able to throw throw this graph into Word for our document here. For that, is that my viewing window that I want to see right here? I think so. So our maximum that's occurring right here. And let me snip this whole thing. Oh, 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 oh. Give me my point back. So the shape of my graph originally a bit wrong, but my overall concept there was right. We went from 0 to 200 as being where the domain of the graph was defined, and that did result in kind of exactly what we were expecting to see right there. I just had my shape wrong, but the idea of that maximum being right there. So it looks like it took here about 24.4 days for salt total. And very technically, I guess you guys are capable of taking the derivative of this function and setting it equal to 0 and solving for that guy right there. That sounds like more of a chore than I'm directly interested in doing right there. So that's why I'm using technology to get that final part of the answer right there. The rest of this problem's hard enough. We don't need to go back and do a whole page of Calc 1 to follow it up right there. So, hey, Cookie Factory asking in chat, what are we modeling here? Here's our problem that we just walked our way through. All right, so again, our units guided us right there. If we didn't have units, I'd have no way to build my differential equation. If we didn't have integrating factors, we'd have no way to solve the differential equation. And now, and I think this is another place where you see in algebra class, people will lead you to believe that quadratic functions for some reason are the only polynomials that matter in life. And we're really proving that wrong right here, seeing that we just had sort of a reasonably legitimate model involving a 26th power, and now recognizing that these very large powers do serve decent algebraic purposes. When you want to create a curve that sort of essentially turns into a straight line, a good way to do that is with an incredibly large power, allowing your terms to eventually go to 0 by taking that large power, allowing the linear component of your solution to be the only thing that's really driving the value anymore, which is why we got that straight line component right there. So interesting thoughts about adding a linear piece to a high order polynomial piece and seeing that on off stuff that's happening right there. So a bit of a bear of a problem right here, but you guys are good with your units. Even when these integrating factor parts come up, you can do an e to an integral power right here. Honestly, the algebra of this is the place where I would expect the most people to encounter mistakes, and not even because you guys can't do this, but because I know exactly what everybody does when they see stuff like this. Like, be like, oh, like I know what your face looks like. We don't have to be in person or online. That doesn't make a difference. Like I'm watching your faces as you do homework in my brain from a distance right here. The algebra here, not the most straightforward algebra we've ever done, despite the fact that it's just algebra right there. But again, we can solve this. We can apply initial conditions. Gosh, this is the grossest constant of integration you're probably ever going to solve for out here. But it actually made sense in the context of our problem because it just involved more powers of 26 with terms that had powers of 26 and stuff like that, right? So what an awesome problem right here. One other thing I would say is I would anticipate, and although I didn't look at it, I'm not going to look at it right now because our video is already long enough. If we were to go throw this differential equation into our differential equation like solver grapher, I am anticipating that it's going to have a really hard time graphing an appropriate solution for us because these 26th powers that are associated with these things, it's going to be really difficult for a numerical solver to take tiny enough X steps in space to not see like huge Y changes out there where we might get more of that zigzagging type stuff that we've seen for some of our solutions. So I'm not going to do it right now just because I want to end the video basically right now. But I would anticipate some potentially not correct looking solution graphs if you guys, and so you guys should go check this out. Throw our differential equation into our differential equation graphers out there. The solution product, our slope field solvers out there, graphers, and see if it gives you something that looks anything close to the solution that we kind of have very good reason to trust, that we just solved for right here. So there's our tough integrating factor example. Where we're going to be at in our next video tomorrow is we're going to talk about changing variables. This changing variables is very much like a graduated version of U sub that you saw in integrals, right? And like your very first fancy integration technique that you learn in Calc 2 is U substitution. This is basically going to be a U substitution to help us solve differential equations. We're going to get some differential equations that just kind of have a bunch of nasty terms in them, but we're going to realize that if we just make a simple substitution, then we can convert a hard differential equation into a much simpler differential equation that we can analyze, and then we can undo the substitution once we have our solutions to then interpret what our solutions of our original differential equation must have been. So this will feel to you analogous like when you learned U sub in Calc 2. And so we're kind of ending chapter 1 with basically just like hey, let's do some algebra swaps to make our problems easier. So tomorrow is a little bit, in a sense, less of a calculus day, more of an algebra day. Today was a pretty tough calculus day, right? This integrating factor is not obvious. It's not something you can easily guess. It's not something you can just kind of do in your head, except for in the easiest of cases. I guess we did get one that you could just do in your head, that integrating factor. I hope that with this one, you guys just look at that and say, oh, it's e to the 5t right there. You can see that one a little bit easier. Most of these integrating factors are not, and you got to actually do the work right there. So that's going to wrap it up for me today. I will see you guys in the next video to wrap up chapter 1 with section 1.9, our U sub for differential equations. That leads us into starting chapter 2 next week, where we're going to begin our consideration of systems of differential equations. At the end of our chapter 2 stuff is also where we're going to get into our little numerical Python programming unit. So I think we're basically doing next week, and then the week after that is where we're going to start with our Python stuff. So I know I've already thrown it up in Canvas last week and for this week. I'm going to put it in again next week for the Python stuff. Like, get set up. Email me if you don't have Python working on your own personal computer or whatever. And in 2 weeks, we'll be hitting that programming unit right there, to create our own differential equation solvers, both in 1 and 2 dimensions, right, with systems of differential equations as well. That's going to wrap it up for me today. I will see you guys in the next video for section 1.9. Have a good one, everybody.